Okay, hello everyone. Today we'll be talking about topological sorting. So you might have heard of this, but topological sort is an algorithm that sorts a directed and acyclic. So what it means to be acyclic is that there is no cycles in the graph. For example, a graph like this, it has a cycle because you go from 1 to 2, 2 to 3, and then 3 to 1, and then it repeats. So you can't sort a graph like this using topological sort. So you sort a directed and acyclic graph into a linear set of vertices so that every edge from one node to another node, the first node comes before the second node. So a quick example of this is, let's just say um, you're waking up. So the first thing you do is you get out of bed, right? So get out of bed is one vert. That just treat this as a node. And then you get out of bed before you brush your teeth. So this is going to have an edge to brushing, right? And then maybe you also wash your hair before brushing your teeth. So there's going to be another edge here. And then maybe you eat breakfast after this. So eat. What this does is you say, because this node and this node, they have no other edges going into them. Therefore, according to this rule right here, that every edge from one node to another node, the first node comes before the second node. These can be the first nodes. So I can say get out of bed is the first node, and then washing hair is the second node, or I can say washing hair is the first node and get out of bed is the second node. It doesn't matter because there are no specific order that you would want for this one, though preferably for this scenario there is no specific order, but if you were to put an edge here, then it's going to have to be get out of bed before washing hair, right? And then if we keep going with this rule right here, we'll find that after washing our hair, and then let's just delete this edge right here because that wasn't originally on the graph. So we'll find that after washing our hair, we have to do brushing. And then after brushing, we'll eat. So this is a possible order after a top sort. Or because we don't have this edge here, the edge here, this one can also be a possible sequence after the sort. So now let's talk about how we can accomplish this, and it's very interesting. Let's go right here. Okay. So as you have noticed, let's start with a new example with 6 nodes. So we'll say n is the number of nodes, and then c is the number of requirements that we want to meet. So let's just say 1 goes before 2, and then 2 goes before 3. 4 also goes before 3, and then let's just say 5 goes after 3, and then 6 goes before 3. Okay, so let's think about how we can satisfy a sort. So what we can do right now is we can just write out the expected answer. So 1 is obviously going to be first, and then it's going to be 2 or 4 or 6 because these also don't have requirements, and then lastly 3 or 5. Now there are also different sequences, right? So the 4 and the 6, they can go before the 2, but they have to be after the 3. So, but they can also be before the 1 if they want, because as you can see right here, there are no requirements pointing into them. So they can technically be wherever they want, but they but 1 has to satisfy that 1 is before 2, but 4 and 6 only has to satisfy that they are before 3, right? Okay, so now that we have this straight, what we can do is we can think about how we can accomplish this. All right, so if you think about it, this is about the in degrees of each node. So in degree is the number of edges pointing to it. So if we can see node 1, let's use a different color here. Node 1 has an in degree of 0. Node 2 has an in degree of 1. Node 3 has an in degree of 3. Node 4 has an in degree of 0. Node 5 has an in degree of 1. And then node 6 has an in degree of 0. So these 0 in degrees means that they have no requirements. So 1, 4, and 6 can be wherever they want in the first 3 positions of the array. So we can say 1 can be here, 4 can be here, and then 6 can be here. They could also be other. They can also be in other places, but for an easiness for topological sort, you typically want these with no requirements to be at the beginning. And then you see that 1 goes to 2, right? So you say, okay, I have processed 1. Now 2 is free of this 1 requirement because 1 is already in front of 2. So you can just knock 1 off of 2 and it becomes 0. And you realize that it's now 0, so you can put it right here. All right. And then 2 goes into 3. So you realize that you processed 2 already, so you can knock 1 off of 3 and then make it 2, right? But you can't add it into the list yet because there are still 2 requirements, and those are 4 and 6. And then now you go to 4. 4 is processed. You can pop it in anywhere, right? And then because 4 gets processed, you knock 1 off of 3, and that becomes 1. But you still can't add because it still has 1 more requirement, which is this 6 right here. And then you go to 5, it can't do it. 6, you realize it's processed, you can put it here, and then knock 1 off of 1, and that becomes 0, and then you realize that 3 is good. So you pop it here, and then you realize that 5, you knock 1 off of 5, and then 5 is good, so then you can put 5 right here. All right, so that's how you can accomplish this. But if you did it that way, you should have gotten this set right here. Okay, so now let's talk about an algorithm. Let's talk about how an algorithm can achieve this. All right, so I'm gonna erase some of these here. And then we'll see what we can do here. Okay, so as you can see, we are going to start the input. My input for this sort is going to be N and C on the first line, and then that means there are N nodes. So N nodes, and then C requirements. So for this input set, we'll have 1 to 2 as an edge, right? And then 2 to 3 as an edge, 4 to 3, 6 to 3, and then 3 to 5. So this N is going to be 6 and 5. Okay, so now you understand the input. We can talk about how we're going to do this. Okay, so imagine that we obviously need an in-degree array to store the in-degrees of each. And we also need an adjacency matrix, right, or adjacency list, because we need to get the edges from each node. So for example, 3 goes to 5. We need to know that because once we process 3, we can subtract 1 out of 5's in degree. So we have to maintain our order of edges. So now what we can do is we take in our input, we build our adjacency lists. In this case, it's 1 to 2, 2 to 3, 4 to 3, 6 to 3, and then 3 to 5. And then we realize that in our in degree, so this is position 0, 1, 2, 3, 4, 5, 6. All right, just make it bigger here. Okay, so we realize that there's nothing at 0 because our nodes are going to be 1 indexed. So let's just mark that off there. Okay, and then for 1, we have 0. For 4, we have 0, and for 6, we have 0. And then as we take in the input, we'll see that each time we see a 3 on the from 2 to 3, we add 1 here, so we'll end up with 3 on the 3 in degree for the node 3, and then we'll have 1 for node 2, and then 1 for node 5. And then what we'll do is first we'll plop all of these 0 in degree nodes into a queue. So the queue has 1, 4, and 6. And then it's gonna push that into our result. So 1 is pushed, and that's out of the queue. Let's just make the queue open-ended here. So, and then it processes its edge, which is 2. So 2 now has an integer of 0 and gets added on to the queue. Right, and then next it processes 4, pops 4 here, goes to here, and then 4 goes to 3, so now it's 2. And then we can move on to 6. So pop 6 out. 6 goes here, makes it 1. And then we can pop 2, put it here, make this 0. Now we add 3 in, right? And then what we can do is we process 3, go here, and then fix 3's edges, and then that becomes 0. And then lastly, put that here, and then pops it out, and it's 5. And now 5 has no 5 doesn't go to any other edges, so now the queue is empty, and then we can quit the program. And then we'll have this perfectly sorted list that is topologically sorted. Okay, so now what we can do is we can head on to IntelliJ and then do some coding. Alright, so right here I imported util because we're probably going to use a queue and then lists, so I just imported it to begin with. And then I'm going to use some global variables just to make our main class look a little nicer. And then right here we're going to need an edge or just an integer because we are not having edge weights. And we'll call this one an array of adjacency lists. All right, okay. And this one is a list of integers for our result. And then we want to have an array of in degrees for each node. And we'll take in our input using counsel, so scanner in, new scanner system.in. Okay. So now we have our in and then c, and it's going to be equal to in that next line. C is going to be equal to next int. Sorry, yeah. All right, and then now we want to allocate our arrays. So in our arrays in our adjacency list. So in degree, we're going to have a size of n+1 because our nodes are 1 indexed. And then adjacency list is the same thing, n+1 as well. Let's just go ahead and suppress the warning for unchecked. All right, there we go. So now what we can do is we have to initialize every list in the adjacency list. So from n or just adjacency list.length, we can do adjacency list at I is equal to this new array list, right? Okay. And afterwards, we can take in our input. So for I is less than C, we can have int from is equal to next int. Int2 is equal to next int. Okay, and then adjacency list at from. We can add it to. We can add the destination node to the position at from, and then we also have to increase the in degree at the destination node. Okay, now that we are finished with these, we can start with our queues. So our queue is going to have we're going to have a linked list. So red. So we want to input a. So this is for all of its edges, right? So its edges, we want to decrease 1 on all of its destination nodes. So for integer edge, for each, we're going to use a for each loop here for simplicity, and then adjacency list at current. First, we have to decrease its in degree, and then we can check if its in degree is now 0. We can push it into the stack. And then this should run by itself, and then at the end, all that we need to do is print out our res array. Okay, so let's test this right now. Alright, so let's just use our example test case here. So we have n of 6 and 5. N of 6 and 5. And then we have 1 goes to 2, 2 goes to 3, 4 goes to 3, 6 goes to 3, and then 3 goes to 5. And we have an exception here, which is quite interesting. Let's see. Oh, yeah, we just have to instantiate our res list. And then it should be good. Let's copy this one. And then we'll run it again. And then, okay, so you see that it's 1, 4, 6, 2, 3, 5. So 1, 4, 6, 2, 3, 5. And as you can see, it fulfills the order because 1 is, let's use a different color because 1 is before 2, 4 is before 3, 6 is before 3, and then 2 is also before 3, and then 3 is before 5. So our order is very good. Now, let's just say, what if you want to prioritize the lesser value nodes first? So your sort will potentially look like 1, 2, 4, 6, 3, 5, right? You still have to maintain the requirements, but you want these free to do stuff nodes to be wherever they are. Even though 2 obviously has to be in front of 1, 4 and 6 could be technically after 2. So what you can do here is you can just change your queue to a priority queue. And then we do have to change this to accommodate a priority queue because priority queue is by itself a class. And now what it will do is it will prioritize the lower elements. And if you want, you can custom sort this priority queue to fit whatever requirements you want, but we can run this again and then we should see a different output array. So yeah, now it does 1, 2, 4, 6, 3, 5 while maintaining the requirements that we've stated above. And this is how you do topological sort, and I hope you enjoyed this video. If you want to see more videos from me, make sure to subscribe and go to my channel page to see more videos. I hope you enjoyed this video and make sure to give it a like. Thanks, and if you have any questions, feel free to post them in the comment section below.